Good evening, everyone, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. Where tonight we're really excited to take a look at some creative solutions for solving equations. I can give you a little bit of a heads up, and I'll tell you that we're going to do a lot with cubic equations tonight, which we typically don't do, so I'm excited to do some new stuff tonight. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. And tonight we're really lucky to be joined by our two panelists, Corey Bennett and Troy Jones. Corey teaches math at New Ames, a state-run charter school in northern Utah. He also trains and consults for Power School and is going to present this summer at Power School University. He's taught mathematics and computer science for 40 years in the public education system, spending nearly 20 of those years in eastern Idaho, pausing briefly to get his master's degree in mathematics and computer science education from Oregon State University. Corey and his wife are parents to 6 children and 24 grandchildren. They live right on the side of the mountain, which affords them a great view of the valley and the Great Salt Lake. They are also miles and miles of trails where Corey loves to hike and bike. He's also an RV enthusiast and has already widely traveled the United States. So Corey, it's great to have you with us tonight.
Thank you. I'm glad to be here.
And Troy teaches math at Westlake High School in Saratoga Springs, Utah. He enjoys helping his students visualize math using dynamic geometry software. When not preparing lessons or grading papers, Troy enjoys camping with his family and cooking with his parabolic reflector oven. That sounds neat, Troy. Thanks for being with us tonight.
Thank you. I'm excited to be here and ready to get going.
Well, that's perfect because you're up first to talk about our agenda for tonight.
All right, so what we're going to do tonight is share some different methods for proving the solution to a cubic equation, and we'll introduce the inspiration when we get to the PowerPoint of why we put together this webinar. We're going to use the TI-Nspire to do some of the activities, and the TI-84 Plus will model on both calculators some of the mathematics that we do, and really want to show some creativity on how we might prove that the solutions to a cubic equation are what they are. And at the end, if you stick around, there's going to be a drawing where your name is entered, and if you are the winner, you will be able to choose from the technology of your choice, the graphing calculator of your choice. Is that right?
Awesome.
Michael?
Yeah, specifically Texas Instruments. So thanks so much for that, Troy. And Corey, can you tell us what we can hope to be able to do by the end of this webinar tonight?
Yeah, the inspiration for the theme here, solving creatively with these solutions, is sometimes our students will solve a problem, we'll give them a problem, and we want them to solve it in a specific way. And we want to show you at least, well, we wanted to show you 99 ways, but we only have an hour. So when you finish here, we hope that you'll recognize and appreciate the student creativity. We're going to apply a varied problem-solving strategies in doing this. Some of them you're going to recognize, and some of them you are going to be blown away. It'll be fun. Troy does a really good job with the dynamic geometry. And then you're going to be able to leverage some of the technology. We're going to give you some of the files that we use to go ahead and solve these solutions.
Corey, thanks so much. We're expecting a large crowd tonight, so your audio is automatically muted. If you have any questions for Corey or Troy, use that Q&A window on the right side of your screen. We'll be keeping an eye on that. We'll be also using the chat window tonight to send general messages. As a reminder, this session is being recorded, and that's going to be pretty important, I think, tonight. The material that Corey and Troy have put together for tonight took me, and it's still taking me a minute to digest, and so I think it's going to be a really great thing to have that recording available at the end so that I can look at it again at my own pace, and you'll be able to do the same thing. All right. Troy, it is all yours.
Great. All right, are you seeing my screen?
Yep, looks good.
Okay, so when when it comes to being creative with mathematics, this mathematician Italo Calvino was commenting on the style of Galileo, and you can read the quote here. He recognized quickness, agility in reasoning, economy in argument, but Galileo's use of imaginative examples. And we hope tonight you might see some different approaches that you might not have thought about before. Now, the inspiration for this webinar, a couple summers ago, I was just browsing around in a used bookstore in downtown, and I picked up this book, 99 Variations on a Proof. And as I was skimming through it, it just stood out to me. I'd never seen a book like this. It took one single equation, a cubic polynomial equation, and showed 99 different ways that you could prove what the solutions are. And so the table of contents I'm going to show here, you can look at the different names. There's a screenplay, topological, flowchart, algorithmic. I highlighted 20 different of my favorite. Between Corey and I, we chose some of our favorite. We're going to attempt to do most of these, but if we don't get to all of them, that's fine. And you'll have access to the slides in the webinar, and there are even a few slides that we created and decided to weed out just in the interest of time anyway. So let's start out with the equation. The question is posed, solve the cubic equation for all of its real solutions. So we have a cubic polynomial. Now, what stands out to you about this equation? You can make some comments in the chat window. You notice there are two sides. The left-hand side is a cubic polynomial. The right-hand side is a linear polynomial. And so I'm going to turn the time over to Corey.
Very good. So what we're looking at here, one of the first ones is the omitted, which is kind of a weird way of starting the thing. But again, the purpose of this presentation is for you to appreciate some of the interesting solutions that we get. So this first one looks like this. If we have our theorem here, you may want to write this down because we're going to refer to this a whole lot. If we have x cubed minus 6x squared plus 11x minus 6 equals 2x minus 2, then x equals 1 or x equals 4. So as we prove this, yeah, the solution is trivial and the proof is left to the reader. I don't know, this reminds me of when I was an undergrad student. And like many of you who majored in math, not only do you take calculus, but you take linear algebra, you take differential equations, you take ring theory, group theory, all sorts of theories. And then you go to high school and you teach algebra. And so you get to miss out on some of the fun math that you used to do when you were in college. So we're going to bring some of that back here. We're going to start off easy first by just using the calculator. So we're going to take a look first here at the CAS calculator and then a little bit at the 84 calculator. So using the CAS calculator, I know some of you are not very familiar with that, but I want to show you why I want this calculator, because I use it in my classroom and I really like it. So we'll start by graphing. We're just going to go over here to, well, let's see. Let's go to New. Usually it asks me if I want to save something, so I'll say no. And then we'll do graphs. And what I want to do is put in the left side. So this is my x cubed minus 6x squared, oops, plus 11x minus 6. That's my left side. Get the arrow out of the way. And you can see how it's graphed. That's very nice. I also see that this label is kind of in the way, and I like dragging it out of here so it doesn't get in the way of what I'm trying to do. To get back so I can put in the other equation, the left-hand side, I press Tab and type in the linear side, 2x minus 2. Okay, so there's my solutions. Again, I'm going to move this a little bit out of the way. It appears, by looking at my calculator, I can see that there is a solution up here and a solution down there. This particular calculator will allow me to go into Menu, Analyze Graph, and find that intersection. To do that, I just go to the left side, where I think it's going to intersect, to the right side, and sure enough, it gives me the 0.46. I think it's important to point out to students what part of this we're actually looking for, which would be the x value. I'm looking at the 4, and I can see the 6. I can also see an intersection down below here, and we'll follow the same procedure. Menu, Analyze Graph, and Intersection. Again, we go just to the left, just to the right, and I can see my intersection here is 1. So it appears that I have 1 and 4 from this graph. Well, that's solving two equations at the same time. What if I were to move this over to the other side and solve? So we're going to do that, introducing a new problem. On the Inspire, you can go Dock, Insert, Problem. This time I'm going to use the calculator. Here we go. Did you notice that it still says F1x? That's because this F1x is associated with this problem and in no way associated with the one before. So as I go to type this in, this is my x cubed minus 6x squared plus 9x, remember because I added it and I'm getting on the same side, minus 4. Okay, as I graph this one, getting the label out of the way, I can see the other side is going to be 0 and I'm looking for my zeros. So I can kind of do the same thing. Menu, Analyze Graph, but this time there's no intersection. So what I do is I use this other command, 0. So I come to this side and that side, and I get the one solution. And then I repeat with the Menu, Analyze Graph, 0, and I can get this other solution. Okay, so that's nice. I can graph and I can see that. I suspect that this one is tangent, that it's a double root. So I want to check this using another feature that's on the calculator. So if I go Menu, whoops, sorry, I don't want to do that. I want to introduce another problem, so let's go Dock, Insert, Problem, and this time I'm going to use a calculator rather than the graphing. So I go Menu, Algebra, I bet I'll be able to solve something here. Okay, my solve is grayed out. And the reason why this is grayed out is because even though I have a CAS calculator, I can choose to turn CAS on and off depending on what activity I have. So in this case, because CAS is off, I can only use numeric solve. But I kind of want to turn CAS on because there's some cool things that we can do with this one. So if I turn on my CAS, I go to my Dock, Settings and Status. I want to go to my document settings, and you'll see there's an operation here to turn the CAS on. So I'm turning my CAS on. Now in this particular problem, it's going to operate. If I go back to my Menu, Algebra, Solve, yeah, now I can type it in. So what I'm going to do is just type in that last one. Here's my x cubed minus 6x squared plus 9x minus 4. And because it's an equation, I have to set it equal to 0. And because I'm solving, and this particular feature of the CAS calculator can also solve literal equations. That means I don't need any numbers, which is fine. But I do have to tell it which variable I'm solving for. So this is comma x. Well, when I solve this, I get 1 and 4. But this is a cubic, and I should have 3 solutions. So even though I use the CAS calculator, it's kind of lied to me because I don't know that I have all the solutions. So we're going to try one more thing on this one. If I go to my Menu, since this is a polynomial, I go to Algebra, Polytools, and I want to find the real roots of the polynomial. So what I can do with this, and some of you have seen this, that I can go up and copy this, so I'm just going to copy it in here. You can see I have way too much in there. So I'm going to get rid of the solve because I'm not really going to solve. And it's not an equation, so I'm going to get rid of that comma x right here, okay? So what I want to do is just find the roots of this thing. Okay. Oh, I knew I needed to take away that 0. Oh, let's go back up. Sorry. Okay, if I get rid of the 0 right here and find the 0, whoops. Got to tell it I want to find the roots of the x. There we go. Comma x. There we go. Now I can see that it gives me 1, 1, and 4. And I know those are the three roots that are there. Well, I like the CAS calculator again because it can give me some of these solutions, but sometimes I have to find them out other ways. So let's take a look now at the TI-84. Right here you can see that I have already typed in both sides of the equation, and when I graph, this should look familiar. On this calculator, however, I want to go second, calc, intersection. So there's my intersection right here. This is a little bit different. I have to move I call it a spider. It kind of looks like that. So I move my spider so that it is right on the solution, or as close as I can get to it. Press enter. My second curve, which is my linear equation, press enter, and then make a good guess. And sure enough, I get 4, 6, which is what I had before. Well, let's see if I can get the ones below. If I go second, calc, and I want to find that intersection again, I'm going to move this down here. Okay, again, press enter for the first curve, enter for the second curve, make a good guess, and it jumps up to the other solution. In other words, it's not going to find this so well. And I'm left there going, okay, so what do I do with this? Well, not to fear, because this calculator has a way to get out of that, and some of you already know what it is. If I go to math, cursor up because it's a little faster, you get to numeric solver. In numeric solver, you can see that I've got the equation. This is the one where I've set it equal to one side and 0 on the other. And so all I have to do here, well, see, it's already given to me. If I clear that out, if I delete that out, and then go and press solve. Well, I don't have a solve here. On the 84, it's prompting me to press the function key. So if I press the function key, it'll go through and it'll solve for the 4. It does not solve for the 1 here. So what I may have to do is actually use another method to get that. And that's what this thing is going to be talking about, is all the different ways that we can use not only the calculator, but mathematics to solve this equation. Troy, tell us about some.
Okay, well, Corey was showing you how we can find the solutions from the graph. And he showed 2 different ways. The intersection of the 2 curves representing the left-hand side and the right-hand side. And then he also put it in maybe what we call a standard form by putting all the terms on one side and 0 on the other side. So what I'd like to do is I'd like to share this document here. And I've graphed the linear function and the cubic function. And when we move everything to one side, we might want to, when we subtract 2 from both sides, I've created a slider here. And so when I drag this slider, you can see both curves. So we're subtracting a 2 from both sides. So we subtract a 2 from the linear function, or add a 2, I should say, it's 2x minus 2. When we add a 2, that's shifting the linear function up by 2 units, but it's also shifting the cubic function up by 2 units. And then if we subtract a 2x from both sides, I can drag this slider right here, and that's changing the slope. So dynamically, we've got a 2x, and if we make this a 0x, you can see that we're transforming these equations so that we're still finding the intersection of 2 curves, but now the cubic function is equal to 0. And so I just wanted to kind of point out that we can do transformations of functions when we're graphing these, and that corresponds to the algebra that we do when we set it equal to 0. Now there's one other type of transformation that we can do. We can translate these left and right. And so I've got a slider here. So let me highlight a few things. When I'm adding a constant to both sides, I'm not changing the solution. The x coordinates, they intersect at the same x coordinates, but it's the y coordinates that are changing because I'm doing a vertical shift. And when I change the slope, I'm not changing the x coordinates, but the y coordinates are changing. But when I do a horizontal translation, now we are changing the x coordinates. And this type of horizontal translation corresponds to a substitution, which we're going to do in our next example. So let me go back to the PowerPoint. And here's another way that we can prove that the solutions are 1 and 4. So the theorem says that if we have this cubic equation, then the solutions are x equals 1 or x equals 4. So the proof, let's start out with this equation. And the first thing I'm going to do is add a 2 to both sides and subtract a 2x from both sides. And remember from the graph, we're just transforming both sides of the equation, the functions on both sides, so that it's in standard form. Now, I'm going to make a substitution. Now, where did this substitution come from? If we already know what the solutions are, let me go back and change these sliders to the original one. So if I had okay, so I'm going to add a 2x to both sides, or subtract a 2x from both sides, I should say. I'm going to add a 2 to both sides. So we haven't changed the x coordinates here. But since I know my solution is 1 and 4, if I move this to the left, I can put one of those solutions at the origin. So when I make this substitution, let x equal m plus 1, I'm just shifting it 1 unit to the left, and that's going to move that one solution to the origin. Now, I can solve for my substituted variable if I expand the cube and expand the square, the cube this first binomial, square this binomial. I can distribute the -6 and distribute the 9. When I combine all like terms, I get this expression here, and that's easy to factor. Take out the m squared, and then use the zero product property, and we get m equals 0, which is the double root, or m equals 3. So by making that substitution, even though the expanding, there's a lot of work, when I refactor it and use the zero product property, it's easy to factor when one of the roots is 0. And then we're interested in our original solution, so then we go back to replace x is equal to m plus 1 and put the value of m 0, and 3 plus 1, and we get the value of 4. So those are our solutions by using the strategy of making a substitution and solving for the substituted variable, and then going back and replace that with the original variable. And you can see from the graphs what was happening on the graph. Okay, another creative solution that I liked in the book, a chromatic proof. So chromatic, what do you think about when you see the word chromatic? Yeah, colors. I'm seeing the chat. Colors. So this is interesting, and I created a document on my TI-Nspire. I'm going to use the color wheel, and I'm using this horizontal line segment as my 0, and I have a slider up here that I can get a central angle. So if I'm rotating by 0 degrees, as I rotate through the color wheel, you see these bars on the right-hand side representing the output for the linear function and the output for the cubic function. And each unit on this scale represents a rotation of 80 degrees. So if I start out here on my linear function, you can see that I'm going negative 80, which would be 1 unit away from the intersection point. But as I rotate, you can watch that bar move up the color scale here so that we get linear representation of a change in colors. And then also, I see a cubic representation in the change of colors. And that linear function has a constant slope, so it's going to keep increasing at a constant rate. But that cubic function, you can see the bar on the cubic scale, it goes up, and then it goes down, and then it goes up, but it increases very rapidly. So there's 2 times when the cubic function and the linear function have the same color. Once when I rotate 0 degrees, which represents 1 on the scale, and then another time when the cubic function goes down, but then it's going to come back up very rapidly, and they both share the color blue at 240 degrees, which would be represented 4 when I convert it to that. So that is a pretty creative way to represent or prove that the solutions are 1 and 4 using colors. Another proof, which I'm going to ask Corey to share, an auditory proof. And so if you look at the musical scale, or the staff, I should say, we can just have each note correspond to the notes A. We can go E flat, B, C, C sharp, D, E flat, E, F, F sharp. Corey, are you sharing yours?
So hopefully they can see the scale. Troy, when you said chromatic, and then we saw the things here for color and sound, I'm sorry, but I started thinking of Close Encounters of the Third Kind, right? When they're at Devil's Tower and they're trying to communicate with the aliens and they flash these colors at them. And then later on they flash sound at them and we're thinking, what are we talking about? Folks, it was mathematics. Let's hear it.
So, hey guys, hang tight for 1 second. So, hey Corey, do me a favor.
Sure.
They have to see the visual for this too. Right now, Corey, I just see your desktop screen. Can you make sure you're sharing the correct monitor? And I think you have a couple.
Oh, got it. Got it. Yeah, let's not do that. Let's share the screen. There we go. Thank you.
Yep, thank you.
Okay, this is the bottom one. This is the linear function.
This is the cubic.
Oh, cubic, sorry. Sounds just like ET, right?
Okay, now before you say anything, go back to the previous slide, Corey. Okay, so the bottom staff represents a linear output on the notes. Each of the notes are just increasing by one note. The upper staff represents the output for a cubic function. And so whoever the composer was that came up with this way of representing the two functions, he chose to play every single note on the chromatic scale, which is the linear function, but then he only chose certain notes as the outputs. So even though there are 54 notes on the linear scale, you could put 54 inputs into the cubic function and get 54 outputs, but he's only choosing certain outputs so that the melody kind of sounds nice together, the two things together. And so Corey played a soundtrack of the linear scale, and then he played an output for the cubic scale. Now we're going to play these together. Okay, so the linear function determines outputs that are notes. The cubic function determines outputs that are notes. And there's 2 times that the score plays the same note, and I've highlighted those in yellow. And it was kind of hard to hear with that slower one, so I've got a quicker one. And as you listen to this, we'll play it a couple times. Listen to the melody for the cubic function, and you'll see that it goes up and then down and then up again, and it increases at a rapid pace going up. So go ahead and play that. One more time and just. So I think that's a pretty creative proof of why the solutions are 1 and 4, because it plays the same note twice in that representation. Okay, I'm going to move on to another proof, so let me get control here.
Sorry. Got carried away. Is that me again?
Yeah.
All right. Go ahead and grab the screen.
Okay. So here is another proof. It's called a wordless proof. And even though it's wordless, I would like to make a few comments on what's going to happen here. So we can represent a cubic polynomial because in 3 dimensions as a volume. So I'm going to start out with a cube that measures x by x by x that has a volume of x cubed. And what we're going to do is we're going to slice this cube apart to do some things to try to create the polynomial that you see above. So the first thing I'm going to do is take off an x squared. And so what you're going to see is in parentheses, you're going to see the previous expression in parentheses, and then what I've subtracted. So when I subtract an x squared, the result is this figure right here, and it doesn't have parentheses, and it shows the dimensions of the resulting solid. So now I'm going to add an x, so I take the previous stuff in parentheses and add an x, and so when I join those two things together and eliminate parentheses, now I've got this polynomial. The expanded form is on top, and the factored form are the dimensions you see here, or at least the dimensions of what each face is. Then we're going to subtract an x squared. That's the way we had to add an x so that we could subtract the x squared now. And so in parentheses was the previous polynomial, and when we subtract x squared, now we can combine the like terms, and this is the resulting solid that we have with its dimensions. So now I'm just going to keep going, and I'm not going to make as many comments, but just see that I'll take this previous polynomial, and we're going to add a 4x, and then this is the result when I combine like terms. Then we're going to subtract 4, and this is the resulting figure. And then we're going to add a 4x, and so when I combine like terms, I get that 9x, a 5x and a 4x add up to be 9x. Now, I can take off a 4x squared, and I'm left with this solid right here. And if we're trying to find the zeros of this polynomial, we can set the factored form or the dimensions equal to 0, the product of the dimensions equal to 0, and we get solutions of 1 and 4. Now, in this case, the 4 wouldn't work in this geometry problem, but I thought that was a really cool way to represent this. The next creative proof is by manner of a word problem. So I'm going to move on to my next slide right here. So the word problem is asking us to, actually let me just advance this. We want to make a box from a 6 by 6 inch piece of paper by cutting out 4 equal squares from the corners and folding up the resulting flaps. If the volume of the box is to be 16 cubic inches, how many inches should we cut out of each corner? So I have a dynamic view. Here's my 6 by 6 inch. This is a three-dimensional view, so I could rotate this and look at it from different angles. In fact, I'm going to auto-rotate it here. And then when I drag the slider, it's going to cut out corners from the box, from the paper, and fold it up to form a box. And so you see the yellow piece of paper with the corners cut out. You see the three-dimensional box when I fold it up. And then I also have a graph of the volume of that box as a function of the side of the square that I cut out of the corners. And so the question says, if we want the volume to be 16 cubic inches, which in this case looks like it might be the maximum volume. As I cut out more and more, it reaches a maximum volume, and then as I continue to cut more, the volume decreases until I don't have any volume left. So with that dynamic view, let's go through the algebra. So the left-hand side represents the volume when I cut out R units from each corner. So I have 6 minus the R, 6 minus 2R would be the length of the box, and 6 minus 2R would be the width of the box, and R would be the height of the box. And so the left-hand side of this equation represents the volume, and if I want the volume to be 16, what do I need to cut out? So I am going to factor a 2 out of each of the binomials and divide by 4 on both sides. Then I can expand the product of the two binomials, and then I can distribute the monomial and then put it in standard form. And then this is the thing that we factored several times previously. And so the factored form, I can use the zero product property to get the solutions of 1 and 4. Now, both of those are solutions to the equation, but in this real life situation, 4 wouldn't make sense because if the edge of the paper is 6 and we cut out 4, we wouldn't have anything left to fold up. So I'm going to turn it over to you, Corey, for the next one.
Okay.
And we might need to cut out a couple of these.
Yeah. So this next one is the student exam. Sometimes our students get really, really creative, and they can go through and do some things. So this one I'm not going to run, but when you get the PowerPoint, you'll be able to see it. What he's going to do is divide both sides by this 2x minus 2. And I have a video here of the thing, but again, just due to time, this is a fairly elementary one that you'll be able to get and view. It's fairly creative because the student starts working with some fractions and all of a sudden gets out of the fractions. So kind of looks like this. Okay, the next one is a two-column proof for those of you who are geometry people. Yeah, you remember this, right? The two-column thing? So what we want to do is just show that we can prove this. Usually we start with the given stuff. And then like we've shown before, we're going to get everything on one side and 0 on the other. Now, I hear my students sometimes say, let's move it over. Well, we don't have a move operation. We have the addition property. So we're going to add a 2 and actually subtract the negative 2x on both sides. Now, usually when I see 4 terms here, I'm thinking factor by grouping. But this isn't very nice to factor by grouping, so I'm going to finagle it a little bit here. I'm going to change this 6 to 1 plus 5 and 9 to 5 plus 4. And then I'm going to distribute. And you can see now I've got 6 terms sitting in here. But look at this. My first 2 terms, my second 2 terms, third 2 terms. You can see I can factor out a greatest common factor here of x minus 1. Pull that out. And I'm left with the x squared minus 5x plus 4. Now using the 0 property, I can go ahead and solve and get this one, which is actually fairly creative for the student to be able to do. Okay, this is an elementary one. Again, the proposition for our cubic. And again, we're getting everything on one side. But this time, very similar to what we did before, I want to do a factor by grouping, so I'm going to finagle that 9x a little bit. And then I'm going to factor the left side, the left part, and the right part. Seeing that I have a common factor here, I can go ahead and factor that out. And just like we did in the last slide, you can see that I can get my solutions of 1 and 4. Troy, tell us about the puzzle.
Okay, so actually, let me share my screen here. I'm going to skip a couple of them I have prepared because there's a geometric proof that I think is really cool. And so I've got a document that I want to share. Okay, any polynomial, it doesn't have to be a cubic polynomial, any polynomial can be represented by what we call a right-angled path. And let me tell you the rules. The length of each segment is going to be a coefficient of the polynomial. So we start out with the highest degree. And if you want to think about starting at the origin, I'm going to start here at point O. And because this polynomial is 1x cubed plus 2x squared plus 9x plus 5, I have a segment of length 1. And then I always want to turn at a 90-degree angle counterclockwise. So when I turn counterclockwise, I'm facing up. And if I have a positive coefficient, I go forward, and a negative coefficient, I go backward. And so I'm going to go up 2 units because that's the coefficient of the x squared term. Then I'm going to turn right again, and I'm facing this direction, and I can go forward 9. And then I turn right again, and I can go forward 5. And so
Troy,
you have a right-angled path that represents this cubic polynomial.
hey Troy.
Yes.
Sorry to interrupt. I don't think we can see the path that you're describing. I just see the geometric PowerPoint slide right now.
Okay, I apologize. All that stuff that I explained, you're going, what is he talking about? Okay, let me do this again.
Troy, I've got it up if you want to see it.
Okay. Now are you seeing it?
Yeah. Yes.
Okay, I apologize. So this might make more sense. here's my right angled path starting at O, and I could do this in a coordinate plane and use this as the origin, but I'm moving 1 unit forward, turn at a right angle, and going 2 units up, turn another right angle counterclockwise, 9 units forward, and turning right angle, and 5 units. And so I've got these sliders so I can change my polynomial. Let's make my leading coefficient something different. So if I drag this, now I have a leading coefficient of 2 or 3. And if it's a negative leading coefficient, I go to the left. So I'm facing towards the positive x-axis if you think of this in a coordinate plane. And a positive coefficient would go forward, and a negative coefficient would be going backward. Okay, now this b, I can change the length of the coefficient of b. So going positive. If it's negative, you can see that I go from O to A is 2 units. That's the leading coefficient of 2. I turn at a 90-degree angle counterclockwise, and I'm facing up, but because it's a negative coefficient, instead of going forward, I go backward. Okay, so the key to understanding this proof is seeing how to represent any polynomial with the right angled path. I can change the coefficient of C. I can change the coefficient of D. Okay, so what I'm going to do is we're going to take our polynomial that's in the standard form, x cubed minus 6x squared plus 9x plus 4, and I've represented that. So the length OA is 1 unit. When I turn counterclockwise, I'd be facing up, but I have to go backwards because it's a negative, so I go down 6 units. And then I turn clockwise again, and I'm facing this direction, and so I go forward 9 units and then 4. So I could change these, but the rule now is I can get from point O to point D, this right-angled path that represents the polynomial. I want to get from O to D with another right-angled path, but the rule is to bounce off each side of these segments, and so I'm going to have 1 segment less. So I had 1, 2, 3, 4 segments because this is a 4 terms in this cubic polynomial. But now I want another right-angled path that gets me to point D with just 3 segments. And so this is not a normal reflection. If O bounces off this side at a normal reflection, the incoming angle and the outgoing angle are the same. But this is not a normal reflection. We want it to be a right-angled path. So I can drag this point P, and you can see that I've constructed this so that I always bounce off that side at a right angle. And I want to arrive at the end point. And so there is one right-angled path that gets me from O to D. And there's another option that gets me from O to D with this right-angled path. Now you can see that as I drag this, we might have different polynomials. And I could drag this to try to find the path that gets me up there. And sometimes it bounces on the extension of that side. So let me go back and change this to the -6. So let's do the algebra now. When I create this right-angled path, I'm creating these triangles that are all right triangles. So I'm looking at this angle. What angle would I have to aim at from O to hit this side so that I end up at D? And whatever that angle that I aim at, then the angle at O and the angle at P are complementary angles. And if this is right angle, then I've got 2 complementary angles, which means that this angle that I've highlighted, the arc, and this angle are congruent angles. They're both complementary to the same angle. So they're congruent to each other. Which means I have these triangles. I got 3 triangles that you see, and all these triangles are similar. They're all right triangles and I've highlighted the angles. So let me go back to my PowerPoint now, and let's look at the proof. Okay, so our theorem is, here's our cubic polynomial. We want to prove that x equals 1 is a solution and x equals 4 is a solution. So I'm going to start and put my polynomial in a standard form. Then I can represent that with this right-angled path. And then I want another right-angled path that starts at O and ends at D. And when my path ends up at D, I've got these two triangles that are similar. Triangle PBQ, that's the second triangle, is similar to triangle AOP, that's the first triangle. And since those are similar triangles, I can form ratios of corresponding sides. And so I didn't know what point P I needed to aim for, so let's just call that X. Okay, so I know that this OA is 1 and this AB is 6. I'm going to aim for a certain point. We're going to call it X. And so this remaining part, PB, is 6 minus X. And when I form the ratios of the corresponding sides, I can solve this for QB and get an expression for QB. So I'm going to put that expression right here. So that's the length of QB in terms of X, the point P the distance from O to P that I need to aim for. Then, if I take 9 minus this expression, I have an expression to represent the length of CQ. And then this remaining side is 4, because that's when we built the polynomial, that had to be 4. Now we've got another pair of similar triangles. Triangle OAP is the first triangle, and QCR, that's the third triangle. Those triangles are similar. So again, I can form ratios of corresponding sides. So I'm going to form the ratio in the small triangle of x over 1. And since x is opposite my marked angle, then the side opposite my marked angle here is 4. So I form the ratio 4 over this expression here. And I can clear the fractions. And I'm going to set this equal to 0. Now we have this expression equal to 0. Let's consider this to be a polynomial. If we were to expand this polynomial, we would actually get the original polynomial up here. But I'm going to call this polynomial, it's not in the normal factored form as the product of linear factors. This is a nested factored form. But I can show that 1 is a solution by evaluating this polynomial at 1. So if we evaluate this polynomial at 1, then I'm going to start with the innermost grouping symbol, the nested parentheses, 6 minus 1. So if that is 1 that we're evaluating at, 6 minus 1 is 5. So that tells us that length is 5. And then when I do 1 times 5, that's going to be 5. So that represents this thing right here. 1 times 5 is 5. And then when I do the 9 minus 4, that represents this whole side of 9 minus the 5, and that gives me 4. And then when I do the 1 times 4, that gives me this expression right here. And then when I add those, I get 0. So this shows me that 1 is a 0 of that polynomial. And I can also evaluate this at 4. And so quickly, we're going to call that value 4. And so 6 minus 4 is 2. So we have the 2. And then when we do 4 times 2, that's 8. So I'm going to represent that as 8. And then if I take 9 minus 8, that's 1. So there's the 1. And 1 times 4 is 4. So that's this side 4. And then when I add those together, I get 0. So that proves that 1 is a solution and 4 is a solution. Now if I am this was a method devised by an Austrian engineer in 1867 named Edward Lill, and he published this method of proving the solutions to this polynomial. So I'm going to take that polynomial that we had in the nested factored form, and I'm just going to write it in a different way. If we were to expand this, we'd have our original polynomial, but we'd have the higher degree terms on the right-hand side. So I'm just going to rewrite it like this. I'm going to commute the terms in the inner parentheses. I'm going to factor out the -1 from both terms, and then all of the addition and all the multiplication, I can commute all those terms. And here's another nested factored form. And if I were to expand this, I could, recover my x cubed minus 6x squared plus 9x minus 4. But this nested factored form is sometimes referred to as Horner's form, the nested factored form of the polynomial. If we evaluate Horner's form, so Horner's form just gives us a quick way to evaluate a polynomial by just addition and multiplication. And I'm going to compare this to the synthetic division algorithm that we use. So if I want to evaluate this nested factored form using Horner's method for x equals 4, I can plug a 4 everywhere there's an x. That's going to be equivalent to the synthetic division of dividing my original polynomial by x minus 4. And so here's kind of the algorithm that we set up, the template. And when I bring down the 1, that represents the coefficient of my x cubed term, 1. And so that 1 is this length up here. Then when I multiply the 1 by 4 and move that up there, that's like multiplying this 1 by 4 to get 4. And that gives me this length. And then when I add the -6 and 4 together, I get -2. And so here's what we see when we evaluate that in Horner's method. And because I'm representing these with lengths, I'm going to use a +2 for this length right here. So 6 and 2 out of, or 4 and 2 out of 6, or 6 minus 4 is 2. So there's a correspondence between the synthetic division algorithm and evaluating using Horner's method and the geometric representation with Lill's method. So 4 times the -2 is a -8, but I'm going to use a +8 for length. And then when I add the 9 and the -8, I get 1. So that 9 minus 8 is 1, which represents that. And then 1 times 4 is 4, which represents that 4. And then when I add those together, I get 0. So here we're showing by synthetic evaluation that 4 is a 0 of the function because we get a remainder of 4. Here's evaluating using Horner's method, and this is the geometric representation. So I think that's so cool that we have a geometric representation of that. Okay, I'm going to take one more quick, there's one more proof using origami, paper folding. So if I share, I can fold this paper. I created this in Nspire. Here I represented the right angled path for the polynomial. And there's a certain fold that I can make. And what I want to do is you cannot construct a solution with compass and straight edge because it involves constructing a cube root, which you can't do with compass and straight edge. But you can fold the solutions. And so the fold that we can do here is we want to make a fold that would make point O be on one edge and point D on B the other edge simultaneously. So we can't do both those at the same time with compass and straight edge. But you can see here that I can fold this paper so that one edge goes through O, and then if I kind of rotate it the right way or drag it, the other edge goes through D. And that is called a Belloc fold. And so I'm going to wrap this up with the Belloc fold would have two lines going through 2 points. And here's the resulting fold, and that gives us the solution at x equals 4, and here's our right-angled path. So I think we're just about out of time here, so Michael?
Awesome. Thanks so much. Sorry, let me just get control back real quick. There we go. All right. So wrapping things up pretty quickly here. Our winner for tonight is Alla Padaloni. I hope I didn't mess that up too bad. We'll be in touch over email, hopefully in the next few days here to get some information from you about which TI graphing calculator you'd like to receive. But again, congratulations on being our webinar winner for tonight. To receive a certificate of attendance, please click the link in the chat window. Also listed is a link for the documents as well, which are going to be super important from tonight, I'm guessing. And if you're watching this on demand, copy that link into your favorite browser to receive your certificate. Do me a favor, when you leave the webinar tonight, you'll automatically receive a pop-up window that will be a survey for tonight. Let us know, what went well and what you'd like to see more of. We'd love to hear your thoughts. And with that, big thanks to Corey and Troy. I realized that I'm not as smart as I thought I was tonight, and that I'm smart enough to know that I'm thankful that this is recorded and I can go back through with that recording a lot slower than I think I'm probably going to need to. So thanks so much for showing some really, really interesting things tonight.
I think we were way too ambitious.
Hey, I'd rather have over-ambitious than the opposite.
But we had fun.
No doubt. Thanks so much, everyone, for joining us tonight. We have one more webinar this spring on Tuesday nights, which will be next Tuesday, the 9th. And then we're going to take a little break for a few weeks in the summer. But please feel free to visit our website to learn more about next week's webinar. And feel free to reach out to us with any questions. Thanks so much again. Have a great night. And we hope to see you back online next week.